15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello, thank you for logging in to listen to another edition of Space Nuts. Great to have your company. I'm your host, Andrew Dunkley, and this week we will be looking at the results of a 16-year study into Einstein's theory of relativity. They've released the results, and it might not come as a surprise to some people, although it might come as a surprise to Einstein himself, because he's looking. He always thought there were holes in his theory, and we're waiting to see if someone can find them. Well, we have the answer, and the process involved in that is very interesting as well. So we'll talk a bit about that. We'll also look at a fairly young star. Well, it's younger than the star that we orbit. It's called EK Draconis, the Dragon Star, and it's basically given us a bit of a look at what the early solar system might have been like. Good thing we weren't around. And Comet Lenny, Comet Leonard is headed our way, and they're not sure if it's going to survive, but we'll see what we can find out about that. Also, audience questions from Ben wanting to know about the energy of the universe, John about the launch of the Webb telescope, the James Webb telescope, and James about odd radio circles. So we'll bump all that off in today's edition of Space Nuts. And of course, joining me as he does every week, whether he likes it or not, is the good Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. No, I don't really like it much, and I don't think I'll give it very long.
It's only been how long now? 4 years?
282 episodes or something.
Yes. Well, this is 283, so
283, there you go.
Here we go.
Yeah, no, it's great. Thank you. Always a pleasure, Andrew.
Now, we might get stuck straight into it because this first story is one that I know a few people are pretty keen on hearing about, and that is a 16-year study into Einstein's theory of relativity and whether or not it holds up. And they found a way to test it, and they've taken 16 years to come up with the results. So where do you want to start, with the process or with the results?
Let's start with why. Because
why?
Because the point about relativity is it is one of the two pillars of our understanding of the universe. Relativity teaches us about the way things behave on large scales and how gravity works. And the other theory, of course, is quantum theory, which tells us about the subatomic world and how particles interact with each other. And the problem is the two are incompatible. Relativity tells us that you can look back to a time when all the matter in energy in the universe was in a single point, but it breaks down completely there because it's got no answers. Quantum theory says that must be what happened. So astronomers and particle physicists, I have to say, are always looking for holes in what you might call the standard model, which is our current understanding. The way particle physicists do this is they try and find new particles. And of course, that's very important with things like dark matter, because dark matter is something whose identity we don't know. And we think it's an as yet unknown subatomic particle that might turn up in one of the world's great particle accelerators. But the other side of it, the study of the accuracy of relativity, that's best done by astronomers. And what you need to do is find regions where there's very high gravity, because we think that it might be in these zones where gravity is really strong, or the gravitational potential is really strong, that we might start to see holes in the theory. Which it would be great, not, with all due respect to Einstein, who was brilliant, and as you said, he knew his theory wasn't complete. But if we found some of that stuff, it would be fantastic. One moment, right? Sent it off. If we could find an error in relativity, it would be fantastic, and Einstein would have been thrilled, because that would open the way for new physics, new physical processes to be understood. And who knows where that might lead? That's the really exciting bit. If we could tease out hidden dimensions or things of this sort, that's kind of where all this stuff is leading, I beg your pardon. All right, so the story today is the Double Pulsar, which itself is a unique object, two pulsars in orbit around one another, which have been known for many years. What are pulsars? They are stars, that basically neutron stars, which are objects less than 20 kilometers across, with almost the mass of at least two suns compressed into that size. So their density is enormous, and they have very strong magnetic fields. Many of them rotate, and they beam out radiation along from their north and south poles, and that gives you this kind of lighthouse effect of flashing beams of radio radiation, and light too in some cases, and that's why they're called pulsars. So the thing about pulsars, though, is that they are incredibly accurate clocks. They're actually better than atomic clocks in terms of their regularity, and that leads to the possibility of doing all kinds of physics. So what we have here is an object known as the Double Pulsar, found actually, using the Parkes radio telescope here in Australia in 2003, and indeed the Parkes radio telescope has contributed to the observations that we're talking about. What you've got is two neutron stars. One goes round 45 times every second, and the other goes round 2.8 times per second with a very high degree of accuracy. And the stars orbit each other once in 2.5 hours. So, this is amazing stuff. These two objects, when you think of them in space, orbiting once every 2.5 hours, each one spinning at these insane rates of spin. And so what relativity says is that because there's incredible accelerations involved in these motions, that they will actually cause gravitational waves to be sent out, the ripples in space-time, and that will slow the system down. And so these two pulsars will do what we've already observed in some situations with LIGO, the Laser Interferometer Gravitational Wave Observatory, and that is a collision of these two. So we're going to look out for the collision of these two pulsars in 85 million years' time. It's quite a while.
Yeah,
but
I might just not stay awake for that.
Yeah, me too. I'd do well to stay awake for 8.5 years, let alone 85 million years. But the bottom line is that it's the fact is that there is energy loss coming from this, and that is all mixed up with the gravitational wave energy, the gravitational wave energy loss. It's mixed up with the theory of relativity, and these pulses of radiation actually allow you to calculate the energy loss. So one of the scientists is Adam Deller, who I think might have been in touch with us, Andrew. Was that right? So I think he might have given us a bell a couple of weeks ago from the OSGRAV, which is the Australian Research Council Centre of Excellence for Gravitational Waves. And they actually have calculated when these pulses of radiation arrive. And Adam says, we modelled the precise arrival times of more than 20 billion of these clock ticks, the pulses, over 16 years. But they've then measured they've then measured the distances to the stars, and actually can sense that there is this wobble in the star's position by actually using other telescopes. In fact, the Very Long Baseline Array in New Mexico. But the bottom line and the answer, which everybody's on the edge of their seat, is that within a precision of, I think it's 99.99
Yep, that's what I read.
It is. It makes it confirms relativity with that sort of accuracy, 99.99%.
So a 16-year study to prove one of the greatest minds in astronomy and science wrong has failed. But that's probably not the way to look at it. It reaffirms his brilliance.
It does. It says that relativity is such an extraordinarily complete theory. There have been other tests done by other means as well, which actually give you higher levels of confidence in it. You can look at accelerations in different ways and get some very, very high accuracy confirmations that relativity is correct. This is yet another one. And it's frustrating in a way because we'd really like to find a hole in relativity.
Well, as you said at the very start, finding a hole in relativity will open up so many other things, so many other areas of study, so much potential for learning.
Yeah. And
we've sort of stumbling over the fact that we're stuck on something we can't prove wrong.
Yes, that's right. That's right. That's what it is.
Frustrating. And it doesn't answer, as you also said, the disparity between relativity and particle physics.
I mean, the two interleave, but there's the quantum theory bit is the bit that, it struggles to be compatible with relativity.
Yeah. Well, I know they're working very hard to try and crack the problem of particle physics and quantum theory, but it's such deep science.
And isn't it intriguing that the techniques that people are using to do that? Who would have thought that two pulsars beaming around one another and spinning around their common center of gravity would allow you to do these tests of relativity? It's actually one of the things that excites me about the Square Kilometer array, Andrew. That's that giant array of radio telescopes, one in Western Australia, one in South Africa, because one of the things that those telescopes will allow us to do is similar science to this using pulsars, but in even more extreme gravitational environments, which the hope is that, yes, the SKA might itself reveal some flaws in relativity, which would open the way for new physics.
We keep talking about it, but it just keeps showing that it's rock solid.
Yeah.
And is it possible we may never solve it?
That's really depressed me, is that? I'm an optimist. Yes, it is possible. Because, it may well be that the thing that reconciles the two theories is so difficult to detect that our instruments are just nowhere near being capable of doing that. But my career started building instruments and optical instruments for telescopes and things of that sort. So I'm an optimist that the instruments will let us do it.
Yeah, and as technology advances and we create new and better and more highly functional instruments that can, get down to the real nitty-gritty of things that we couldn't even imagine 10, 15, 20 years ago, it might just make the discovery of a flaw in relativity that much easier to find.
Yes,
but it might take a long time. We might not crack it in the next decade. We might crack it in 30, 50, 100. Who knows? I don't know.
Yeah, as long as it doesn't take 85 or 86 million years to crack it, and I'll still be interested.
Yep. It keeps your brain going, and it'll of course prompt a batch of questions about particle physics and quantum theory, and I'm sure we'll get a dark energy and a dark matter question here or there because they're all wrapped up in it, aren't they?
Yeah, that's right. That, one of the that's how we know that these theories are not perfect, because we can't identify dark matter yet and dark energy, the energy of the universe. Yeah.
But we just know they're there.
Yes,
science
so all the evidence is that they're there.
Proves it.
Yeah.
Yeah. All right. If you'd like to read that study, it's being published in all manner of websites and news releases, but it's well worth a read. I've read the whole thing, 2,300 pages worth. Actually, I read the media release. That was 2 pages.
Yeah. That's courtesy of CSIRO, the Australian Science Agency or Science Organisation, and a shout out to them, because they very kindly, when there's a big story like this, they send it our way, which is good.
Yep, indeed. And it was good to be able to talk about it, but well worth looking into if you're really keen on learning more about how they did it. And even though we know they didn't find a flaw in the theory as yet, but I suppose, as we've been saying time and time again, watch this space. This is Space Nuts with Andrew Dunkley and Professor Fred Watson. Now let's take a little break from the program to talk to you about our sponsor NordVPN. Now, as a Space Nuts listener, NordVPN is offering, for a limited time only, 73% off a 2-year plan. That's a very, very good deal. And you can take advantage of that right now just because you're a Space Nuts listener. Now, there is also a 30-day money-back guarantee. That in itself is pretty darn impressive. Now, if you'd like to take advantage of the offer, just go to the special URL that's been created for you, which is nordvpn.com/spacenuts. That's nordvpn.com/spacenuts. Look over the deal, see what you think, and then give it a try. 30 days money-back guarantee, and if you don't like it, you don't like it. But it is a really good service, and it enables you to secure your internet access from hackers, from people trying to steal your banking information, from people trying to get hold of your money. It also gives you that ability to access areas that are outside your geographical zone. So it really is a great service, and one worth taking a look at. And look, it's going to cost you very little on a week-by-week basis. So you get 1 month free if you buy a 2-year plan, and a 73% discount on the 2-year plan. So if you want to grab the deal, it's nordvpn.com/spacenuts. That's nordvpn.com/spacenuts. And just a reminder that if you're in Australia and you're looking at that URL and checking out the prices, they are in US dollars. So just be aware of that. But just to give you an idea of the cost, under this deal, as a Space Nuts listener, $3.16 a month. That's US dollars. $3.16 a month. That's $79 for 2 years. Normally, you'd pay nearly $300. So check it out today at nordvpn.com/spacenuts. Nearly got there. Now back to the show.
0G, and I feel fine.
Space Nuts.
Thanks for joining us on Space Nuts. And now, Fred, we're going to talk about this youngish star that they say gives us insight into the early solar system. This is EK Draconis. I love the name of it. Sounds like something out of, what was that show? I can't remember.
Sounds like somebody's name, doesn't it? EK Draconis.
I quite like it.
Yeah. Actually, the name tells you that it's a variable star, because stars
Game of Thrones.
Yeah, I've never watched the Game of Thrones, so I can't comment on that. But yes, it does sound like something that will belong there. Any star that's got 2 letters in front of its name and a constellation, Draconis means it's in the constellation of Draco, which is a northern hemisphere constellation. But that tells you it's a variable star. That's it's the category that astronomers use to discuss them, like RR Lyrae and Delta Cephei and things like that. The letter and two letters. So Delta Cephei is not one, but anything with 2 letters and a constellation name after is a variable star. And so that ties in with what we know about this object, which is relatively close by. I'm not sure its exact distance. It's measured in tens of light years rather than millions of light years. But it is a young star, a youthful star, probably less than 100 million years old. And that sounds pretty antique to we humans. But when you think our sun is about 4.57 billion years old, that puts it into perspective. But we believe the sun was a bit like EK Draconis, when it was a youngster. And so the more we can find out about stars like this, the more we can learn about the environment that the planets faced in the earliest days of the solar system. And what people have long thought is that stars like this basically regularly emit these huge high-energy clouds of charged particles, of subatomic particles, which are called a coronal mass ejection.
Yeah.
And that's, or CME. We see them as what are called flare stars. In fact, right at the start of my career, I worked with a colleague, Brad Carter, up in Queensland, whose topic there was flare stars, which was interesting because we had the instrument I'd built to do this was called FLARE, but that was two different spellings of the word. And we observed flare stars with FLARE, and they're young stars of a particular type. So EK Draconis is one of these. We know that they flare in energy. That's why it's known as a variable star. But we now have much more, sophistication in the instruments at our disposal. Just as you were saying in relation to gravitational waves and understanding relativity, we've got things like TESS, the NASA Transiting Exoplanet Survey satellite, and we've got other big telescopes equipped with actually very sensitive equipment like spectrographs for measuring things like velocity. And what these observers, and this is a group led by scientists in the USA, is actually in the University of Colorado, I think that's where some of the authors are from. What they've done is they've used TESS and found basically a flare of light, and in fact they call it a super flare because it was very bright. But then they followed up with an observation that essentially allowed them to see this coronal mass ejection heading our way from the star's surface at about 440 kilometers per second, something like that.
How far away is this thing?
Its distance is measured in tens of light years. I don't have an exact figure because I didn't bother looking it up, which I should have done because I knew you'd ask that question. But it's far enough away that this is not going to affect us, Andrew. But any planets in orbit around EK Draconis could well get drenched in these subatomic particles. Lots of things could fry, particularly if said planets have any intelligent species of life on them who have developed electronics and electricity, because that literally fries. And in fact, one of the biggest events of this kind that has been recorded on Earth, I think you and I have spoken about it before. It happened in September 1859. I remember it well.
Yes.
And it's called the Carrington Event. So September 1859, we were nowhere near in the world as dependent on electronics as we are today. But it still caused telegraph lines, in the United States where this newfangled telegraph was coming into being. The telegraph lines just basically caught fire because they got very hot and were, near the wooden poles and the insulators. It actually it destroyed quite a lot of the youthful network of telegraphs that were growing up, probably here in Australia as well, but certainly in the USA. That was where the biggest effects were, and that's the kind of thing that would happen. That was the biggest event and a suspected coronal mass ejection known to have hit the Earth. Almost certainly bigger ones will have hit in the past, and certainly in the sun's youth when it was delivering these things all the time. So it's a salutary lesson by observing EK Draconis that we can find kind of what happens. The thinking that comes about, and I should have said this outburst I just mentioned was in April 2020. The thinking is that it was more than 10 times bigger than the Carrington event, but that doesn't necessarily mean that we might not face one. So it behoves our electrical and electronic engineers to bear in mind that one day you could have this flux of subatomic particles that could blow fuses everywhere. It certainly is very relevant to space communications, because spacecraft are, of course, they're outside, well, the ones that are outside the magnetosphere of the Earth, which is the geostationary satellites, they would be first cab off the rank in getting fried. And that's why these spacecraft are often, there's often quite a bit of what you might call armoring. It's not quite lead, but that sort of thing to try and protect the electronics from the intense radiation field that they're in.
Yeah, to try and help people understand how very real the threat is to electronics on Earth of some kind of CME, it is something that emergency authorities around the world are actually gearing up for, because there is always the danger that we will get clobbered by one of these things. And it doesn't have to be the size of the one we were just talking about on the star Draconis. But and as you said, it's unlikely our sun will ever do anything that big, but you can't absolutely write off the possibility. CMEs are a big threat to us now because of our reliance on electronics. That Carrington event, it affected telegraph lines, but now we have so many things that are attached to an electrical grid that are day-to-day factors in our lives that we are so 100% reliant on, including what you and I are doing right now.
Yes, exactly.
A big coronal mass ejection direct hit could completely wipe out some of the grids and cause extensive and billions of dollars worth of damage. That's worst case scenario. But emergency authorities, even the authorities in this little town that I live in, have been looking at this as a potential problem in the future, and that it needs to be something that we factor into future emergency coverage and dealing with the potential fallout from the loss of widespread electronic reliance. And it does make you sort of pause for a moment, because we take so much for granted, and at the whim of the sun, it could all just be taken away from us. And we need to really consider the possibility. And, the other day, probably about a month ago, I was just sort of scouring through some websites, and I saw this little banner, emergency banner on a website. And I thought, oh, what's this? And it was, in fact, a warning about a potential coronal mass ejection event that could affect electronics in the Northern Hemisphere.
There you go.
So, it's already something that's being taken quite seriously. Yeah,
and you're a follower of the space weather website as well. Yeah, because this is all what we call space weather today. It was certainly 50 years ago, nobody would ever dreamt of talking about space weather, but that's what we've got. We've got this environment that the Earth is in that has stuff mostly coming from the sun that causes changes in the flux of particles. So yes, something hard really hitting us would cause damage, and it's right for people to be aware of it. So I mean, it's a good news story when you know that authorities are actually cognizant of this, that they might need to deal with a situation where the world's electronics are effectively wiped out.
It could happen. Yeah. Don't ever write up the possibility. There are so many things that we just don't even think about, but there are people who are thinking about it and looking for ways around it. So that's reassuring. But learning the potential of things through observation of stars like this is certainly a great way to get ourselves ahead of the curve in terms of dealing with future potential problems. Most likely won't, but never say never, and that's kind of where we're at. So we'll move on from that, Fred, to Comet Lenny. I'm calling it Comet Lenny. Comet Leonard, could be Leonard. We're not sure, but this one's hurtling towards us now. And a couple of things that are very interesting about this particular comet. And for those in the northern hemisphere, bad luck, it's going to drop out of your vision. And we in the southern hemisphere will get a really good look at it in the next week or two.
That's correct. So it's been known about since the beginning of the year, actually. It was discovered by astronomer Greg Leonard. I hope I'm pronouncing his name correctly. Astronomers always take the names, comets always take the names of their discoverers. So starting with Halley and working upwards. It's an object which has come from the depths of the solar system. It's in an orbit that is very, very stretched. At its furthest, it would be 3,700 times further away from the sun than we are, which is way, way out, almost at the level of the Oort cloud. Not quite. It's probably not the first time this comet's come into the centre of the solar system, but it's a rare visitor, and it has kind of brightened up and become relatively visible within the northern hemisphere over the last couple of weeks or so. It's about 1 kilometre across, its nucleus. And of course, comets, as we've said many times before, comets are like cats. They have tails and do anything they like. Yeah. The thing about comets is, yes, you can predict sort of where they're going to go because they act under the gravity of the sun and the other planets. But you can't predict whether they're going to become particularly bright. And so...
And that's true. Last time Halley's Comet was here in the late 80s, it didn't really do what everyone thought it would do. It was very disappointing. Actually, from a naked eye point of view.
Yeah, although we did know that back in 1910 when it was here last time. It's because it was on the wrong side of the sun. But you're right, you can't predict. And one of the things you can't predict is a comet. Quite often, a comet looks quite promising as it comes in from the outer solar system, starts brightening up as it gets near the sun, and then falls to bits under the effects of the sun's gravity. Breaks apart.
And that might happen to this one.
Yes, there's a worry that it might. It's however, as far as we know, it's hanging together and will appear in southern skies from about the 17th of December, a few days' time. So hopefully anybody in the northern hemisphere who's got the wherewithal to find it, and you can easily find where it is by Googling the name, it will be worth a look. Its closest to Earth is 12th of December. That's now gone. It's on its way away from Earth, but is not yet closest to the sun. I think it gets closest to the sun on the 3rd of January. That's its closest approach. So
I also read that when it gets near Venus, it'll be the closest in recorded history that a comet has ever been to Venus.
Yes, that's right. 4 million kilometres of Venus. That, if you're on Venus and you could see through the terrible atmosphere that Venus has got, it would be a spectacular sight. It would be very spectacular. Actually, one of the nice things is that Venus is pretty obvious in our skies at the moment. It's the brightest thing in the early evening sky. It's drawing closer to the sun in the sky as it passes between the Earth and the sun, which it will do at the end of the month. But Comet Leonard is pretty close to Venus in the sky, so it's a good guide to try and find it. And I'll be looking, if the skies are clear, on the 18th of December or thereabouts, 17th or 18th, I'll have the binoculars out looking for an object to the south of Venus and try and find it. And I'll let you know.
There's something for all the sky watchers and amateur astronomers that want to see if they can get a good view of Comet Leonard. This is Space Nuts. You're with Andrew Dunkley and Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
A reminder, if you'd like to become a patron, jump on our website, spacenutspodcast.com or spacenuts.io, and click on the supporter link. And you can become a patron through Patreon, through Supercast, or you can just buy us a cup of coffee. There's a link specifically there that says, buy us a cup of coffee. So if you want to do that, those are the options available. And thank you to all of those who recently signed up for Patreon, because, our numbers are growing, and that is fantastic. And don't forget, I think there's still a 30-day trial for Patreon and Supercast, so you can sign up. You can decide whether or not you like it. And if you do, great. If you don't, that's fine too. It's all explained on our website, spacenutspodcast.com or spacenuts.io. Now, Fred, we've got some questions to go through. We're going to do a couple of text questions and finish off with an audio question. And this first one comes from Ben in Port Lincoln, South Australia. Hi, Fred and Andrew. I really enjoy your show and look forward to each new episode. I have a question about the energy in the universe. Have they tried to estimate how much there is? Do they, scientists, think that there is new energy being made? And we can't have a question that doesn't involve black holes. So if black holes suck everything in, have they found, or are they looking for the opposite to a black hole? Thanks again for your great show. And Andrew, if you ever come to Port Lincoln, I'll be keen for a round of golf. Ooh, is that a threat? That'd be great. Thank you, Ben. We are in South Australia in February, but I don't think we're getting anywhere near Port Lincoln, but maybe one day.
You might have to make
the first part of his question was about the energy of the universe. Is there new energy being created? And, how much is there?
Actually, it is a really interesting question that's got a fairly complex answer. But the overall energy of the universe is probably, wait for it, Andrew, 0. Ta-da!
I knew you were going to say that. I knew you were going to say that.
Yeah.
I don't know why. But...
and it comes about, it almost sounds like, spreadsheet economics, but yes, there are about 10 to the power 80 particles in the observable universe, and these are subatomic particles mostly. It's not as big a number as you might expect. And they have got colossal amounts of energy because E equals mc squared. So these particles have huge amounts of energy. And if you think of light or electromagnetic energy, matter and antimatter, they all have their own energy, which is often called positive energy. But there is a sort of opposite of this, something that's called negative energy. And that essentially is stored in it's the gravitational attraction that exists between all the positive energy particles, which balances the negative force. And so the answer is, on this sort of arithmetic, there is no universe energy at all. So, it sounds crazy. There is the source that I've been reading about this quotes Stephen Hawking in his Theory of Everything book to explain the concept of negative energy. And I'm quoting now from the book. 2 pieces of matter that are close to each other have less positive energy than the same 2 pieces a long way apart, because you have to expend energy to separate them against the gravitational force that is pulling them together. And that gravitational force is what the negative energy is. So it is a bit counterintuitive that you'd think that 2 pieces of matter close together would have more energy than if they were a long way apart. But it's all about the energy that you have to expend to separate them. So it's quite a nice analog. So it's a difficult area to talk about without bringing in the mathematics. I might actually try and quote another pair of astrophysicists, and I think this is from one of their books. It's Alexei Filipenko and Jay Pasahoff, both US scientists, well-known ones. They explain gravity's negative energy, and it's actually not a book, it's in an essay, which is called A Universe from Nothing. They explain it like this. If you drop a ball from rest, which is defined to be a state of 0 energy, it gains energy of motion, which is kinetic energy, as it falls. But this is exactly balanced by the larger negative gravitational energy as it comes closer to the Earth's center. So the sum of those two energies remains zero.
Gotcha.
Yeah. So that's the first part of Ben's question. The second part.
Are they looking for the opposite of a black hole, which I think we've had questions about before? Are we looking for a white hole? I think was right. Yeah.
So a white hole is what you get when you take the relativistic equations that define a black hole and you make time negative, you make time flow the other way. And what you get is a white hole. And there's no physical reason why that should not exist. The mathematics works. A white hole, whereas a black hole sucks things in and won't let anything out, a white hole spews things out but won't let anything in. But the bottom line is a white hole has never been observed. There is no astrophysical object that could be deemed to be a white hole. So it may well be that these things are prevented from existing somehow. And while the mathematics are terribly elegant and work well, they don't reflect reality.
Okay. Interesting. That is until we find one.
Until we find one, yeah.
Thank you, Ben, and happy golfing. Let's move on to John, who is in the good state of New South Wales. Just wondering why the James Webb telescope was shipped to French Guiana to be launched. I've seen a couple of reasons, such as it uses less fuel to launch at the equator and it's part of ESA's contribution to the project. Maybe it's a bit of both. Love your podcast. Thanks, John. Has he answered his own question?
Yes, he has. John, you're right on the money with both of those. So ESA's main launch site is there, not very far from the equator. And of course, the reason why you want to launch satellites into orbit from the equator is because you're taking advantage of the Earth's rotation, which gives at the equator about a 1,600 kilometre an hour additional free gift in the velocity that you need to go into orbit. So that's what it's all about. Exactly as you've said, both of those reasons.
Okay, easy peasy, John. I read an article today about whether or not humanity will ever achieve 1% of light speed, and it was really interesting because they tried to explain how you could achieve it. And they came up with ideas going forward about warp drive and using light sails, which they reckon could ultimately achieve 10% of light speed in a nuclear fusion as a propulsion system. But the problem with achieving 1% light speed is the energy required. And you and I have talked about if you wanted to achieve light speed, there's not enough energy in the universe to do it.
Quite.
And to achieve 1% of light speed, they said you would need to expend the same amount of energy as 2 million human beings would expel in a day.
Yeah, there you go.
That's the energy required to reach 1% of light speed. Yeah. So getting a gravity boost or a boost by launching at the equator makes a hell of a lot of sense when you know what sort of energy is involved in just getting to the speed you need to get out of the Earth's atmosphere. So it's all relative. Boom, boom. Let's go to our next question. This one comes from James in Cincinnati.
Hello, Mr. Dunkley and Professor Watson. James from Cincinnati, USA, and I've got some odd questions. I haven't heard y'all speak much, if at all, about odd radio circles, which were discovered using your very own ASCAP, and I wanted to know the good professor's thoughts on the subject. What do you think could be the source of them? They all appear to be encircling galaxies, so would it be likely that supermassive black holes are the cause? If so, why don't we see more of them, since supermassive black holes seem to be the center of all galaxies? A few of them do not appear to have galaxies, at least visible to us at their center. Do you think the James Webb Space Telescope will be able to tease out any information to this odd mystery? Thanks. Love your show. It gets me through my daily work commute.
Thank you, James. And go the Bengals, my favourite American football team. And James, great radio voice, by the way, I might add. That's, you sound great. Okay, odd radio circles. I think we have come across these before, but we haven't spoken about them in a while.
No, that's right. And they're a great advert for the Australian Square Kilometer Array Pathfinder, a radio telescope array in Western Australia, which is a Pathfinder for the Square Kilometer Array, operated by CSIRO. Once again, we're bookending this segment with CSIRO, the Australian Science Agency. So they were detected back in 2019 from basically one of the pilot surveys of something called EMU, which is a great Australian name, and it's an acronym for the Evolutionary Map of the Universe. And it's basically those data have come from ASCAP. This was only the pilot survey, so it wasn't the final EMU. This was just things that were, the sky that was being studied, just to check that all was good for the main survey. And these things turned up. The astronomer who discovered them was Anna Kopinska, but one of the astronomers who's written a lot about them, and I suspect who chose the name, because that is very much the kind of person he is a good friend of mine, Ray Norris, now with the University of with Western Sydney University, formerly of CSIRO. And that's how Odd Radio Circles sounds like a very Ray name. What are they? Well, exactly what they are. They are circular features, roughly circular features in radio waves, which are brighter along their edges and, as James mentioned, often have a galaxy at their center. And that's interesting because, it's, anything that's bright around its edges speaks of it possibly being a bubble. Because if you look at a bubble, a bubble that you blow from soap or something like that, all you see is its edges. You don't see the near and far sides, not normally anyway. So bubbles show up often as brighter around their edges. But the problem is that they are quite big. These are typically 1 minute of arc in diameter. That's a minute of arc is what? It's a 16th. It's a 30th of the diameter. No, it's not. It's a 15th of the diameter of the moon. Do the sums properly, Fred. The moon's about half a degree in diameter, which is 30 minutes of arc. So half of that would be 15. What did I say? I can't remember. Anyway, 1 arc minute. It's a small amount, a 30th of the diameter of the moon. There you are. I'll get the right answer eventually. So they're big, and if it's a shock wave or something to do with an energetic event like a supermassive black hole at the center of a galaxy, it would have taken a long, long time for these things to get to the size. So the problem is that the studies that have been done don't really seem to fit any of the things that you would expect: fast radio bursts or a gamma ray burst or a supernova remnant, something of that sort. That's typically spherical or often spherical, or even a planetary nebula, which is the shell that forms around an old star of the same sort of size as the sun is. That's what our sun will do eventually, form one of these planetary nebulae. So it's a very interesting thing. And I'm not an expert on odd radio circles, but I don't think the science has progressed really all that far, apart from the fact that several have been discovered. It may even be more than 10 now. Bright at radio wavelengths, not visible infrared or X-ray wavelengths. It's fascinating. So, James, thank you for reminding us that there are things in the universe that we simply don't yet understand.
Plenty of them.
I mean, the alignment of galaxies in their centers could simply be an accident. You've just got, I think, 3 of them have galaxies at their centers, which, would associate them, you would think, with the galaxies, but that might be a chance alignment. We don't know. These things might be in the foreground.
Could be a coinkydink.
Yeah, coinkydink. That's right.
Indeed. All right, James, lovely to hear from you, and thank you for your question, odd as it was. And by the way, Fred, EK Draconis is 111.32 light years from Earth.
What did I say? A few tens of light years away.
A few tens of light years. Yeah. It's 11 tens of light years.
It is. Thank you, Andrew. Thanks for looking it up.
No problem. That brings us to the end. Don't forget, if you want to get in touch with us, visit our website and you can send us an email or you can send us a voice message or you can send us a voice question. Just log on to spacenutspodcast.com and click on the AMA tab or the send us a question link on the right-hand side of the homepage. Whatever you want to do, we'd love to hear from you. Don't forget to tell us who you are and where you're from. And while you're online, visit the Space Nuts shop because there's all sorts of goodies like that. That's the Space Nuts sticker. I saw a bucket hat the other day while I was scrolling through the list of things. There's all sorts of goodies on the Space Nuts shop. It's not too late to order for Christmas. It won't turn up till next Christmas, but you can still do it. Or maybe just get yourself something so that you can be a proud space nut and wear your badge with honour. That brings us to the end of another show. Fred, thank you so much.
Great pleasure, Andrew. Always good. And I think we'll be talking next week by the sound of things.
We will. Yes, we will indeed. Good to catch up. See you soon. That is Professor Fred Watson, astronomer at large, part of the team here at Space Nuts. And back to Hugh in the studio, who's got a lot of patchwork to do on this episode. Got to tell you. See, you didn't think anything went wrong. And from me, Andrew Dunkley, thank you so much for joining us. We'll catch you on the very next episode. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.